3.4 complex numbers. A complex number is an expression of the form a plus bi, where a and b are real numbers, and I squared goes to -1. A is the real part, whereas b is the imaginary part. If two complex numbers are equal if and only if their equal parts are equal and their imaginary parts are equal. So in 12 minus 6i, 12 is the real part, and the imaginary part is -6. In 8i, 8 is the imaginary part. If there is no term with I, then there are no imaginary parts. We can do basic arithmetic operations on complex. I don't know why it keeps saying complete numbers. So 3 minus 5i plus 12 plus 3i. We add them just like terms. We can add 3 and 12 and get 15. -5i plus 3i goes to -2i. These are not like terms because this is imaginary and this is real, so that's as simplified as we can get. We also write the imaginary number last. 8 minus 7i minus 3 plus 9i. I like to distribute the negative first. -3, 9i, and now it's back to adding, so we get 5 minus 16i. 2 plus 4i times 6 minus 3i. We're going to have to FOIL. 2 times 6 is 12. 2 times -3i, -6i. 4i times 6, -24i. 4i times -3i goes to -12i squared. But we said earlier I squared is -1. So it goes to -12 times -1, which is 12. So we combine our like terms now, and the 12s will cancel. And we are left with -30i. Before we go on to dividing, let's talk about I to powers. I to the first is just I. I squared is -1. I cubed goes to I squared times I, which becomes -I. I to the fourth goes to I squared times I squared, which goes to -1 times -1, which goes to a +1. I to the fifth, we break it down as I to the fourth times I, which goes 1 times I, which is I. I to the sixth, we want to break it down as I to the fourth times I squared. 1 times -1 goes to -1. You can see a pattern developing I, negative 1, negative I, 1, I, negative 1. What's going to be the next in sequence? Dividing complex numbers. To simplify the quotient a plus vi over c plus di, multiply the numerator and the denominator by the complex conjugate of the denominator. In general, when you have a plus vi over c plus di, the conjugate of the denominator is where you change the middle sign, c minus di. So this is going to end up giving us AC plus BD plus BC minus AD times I all over C squared plus D squared. The denominator is a sum and difference pattern, except you're going to have an I squared. That goes to negative 1. Normally it's a minus in the middle, but a minus and negative turns to a positive. That's where the plus comes from. So if we start with our example, 6 minus 3i over 5i. Now there's only one term in the denominator, so we multiply by its conjugate, which is a negative 5i. So on the numerator, I'm going to distribute. On the bottom, I'll multiply negative 25i squared. We can simplify. And we can even break this up and reduce it. So it's really negative 15 plus minus 30i over 25. We could take out a GCF of 5 from everywhere. Or you could split it up into two fractions. Our next example, 2 minus 4i over 3 plus 3i. Multiply by the conjugate, 3 minus 3i. Now we can use the shortcut. The shortcut said a plus bi times c minus di. And it becomes AC plus BD plus BC minus ADI. If you don't like the shortcut, you don't need to use it. You could just FOIL as normal. A is 2, B is negative 4, C is 3, and D is 3. So we got 2 times 3 plus negative 4 times 3 plus negative 4 times 3 minus 2 times 3i over, and this goes to c squared 3 squared plus d squared 3 squared. Simplify. 6 minus 12 plus negative 12 minus 6i over 9 plus 9. We get negative 6 minus 18i over 18. We can reduce all terms by 6 to go to negative 1 minus 3i over 3. When taking square roots of negative numbers in general, the square root of negative 1 is I. Square root of negative 25, negative 5. I'm sorry, 5i. Square root of negative 28 goes to 2i root 7. So for multiplying two binomials that have roots, we're going to FOIL root 6 times 3. You cannot multiply one number that's in a root times one that's out, so it just goes 3 root 6. Root 6 times root negative 8. You combine the numbers in the roots, they're multiplying. Be plus root negative 48. So we bring out the I. 48 goes into 16 and 3, so it goes to 4i root 3. Plus root 3 times 3, so plus 3 root 3. And L for last. Root 3 times root negative 8. Combine it to get negative root negative 24, which becomes 2i root 6. Now we look for our like terms. Like terms need to have the same root. So in the blue we have a 3 root 6, and in the purple we have a 2i root 6. So we can combine those to be 3 plus 2i root 6 plus, and then our next two also have same root, root 3. So plus 3 plus 4i root 3. When solving complex quadratics, you could either solve using square roots or use a quadratic formula. I know to solve this one using square roots by subtracting 25 from both sides. Get x squared equals negative 25. Next step is to square root. So x equals root negative 25, which we said earlier goes to plus or minus 5i. Our last example, x to the fourth minus 4x plus 5 equals 0. Now we cannot solve this by factoring, so we're going to use the quadratic formula. A is 1, b is negative 4, c is 5. So x equals negative b, so positive 4 plus or minus the square root of b squared negative 4 squared minus 4 times a times c all over 2a. 4 plus or minus 16 minus 20 over 2. 16 minus 20 is negative 4. We're going to take out the I and get 2I. 4 plus or minus 2I over 2. Everything can be reduced by 2 because it's not in a square root, cannot reduce within a square root. So we can get 2 plus or minus I.